Okay, this is a What the Physics video on circular motion. This has been, this is like the second day or second session of it. The first one was all about just the basics of circular motion, focusing on speed and velocity. And this one we're going to be focusing on more along the lines of force and acceleration. But before we do that, I would like us to summarize, compare, contrast whatever we can about different types of speed that goes along with tangential speed, translational speed, and rotational speed. So, what can we say? And yes.
When rotational speed increases, tangential speed increases.
Okay, so when rotational speed increases, the tangential speed increases. Is that what you said? Okay. Yes, I would say that is in general the case, but I do want to put on a little caveat there. That is assuming there's no movement along the radius of the object. Okay, so if you're not moving further out from the axis of rotation or closer in, then yes, they're going to be nice and proportional. Okay, excellent. What else? Yes. Okay, so rotational speed is measured in rotations per minute, or usually we'd actually say rotations per second. Okay, and if you recall, we've also talked about frequency, which is the number of occurrences per time. So, like saying rotations per second. Okay, as opposed to period, which is how long it takes for one rotation to occur. So yeah, that's rotational speed. And then we had tangential speed, which is when we're talking about a particular point on the spinning object. And we're saying, oh, that's going at this speed, as in it covers this much distance in this much time. So that is going to be in meters per second. That's a good point. Good to focus on units too. Okay, how about one more, please? And one more. Oh, thank you. Yes.
If you have a tire that is spinning, the farthest point from the axis would have the greatest tangential speed, but all the points on the tire would have the same rotational speed.
Okay, so to repeat that in case it wasn't loud enough, if you have a spinning tire, the point farthest away from the axis of rotation is going to be going the fastest in terms of tangential speed. Okay, and the closer in you are, the slower you're going to be going tangentially. But if you're talking about the rotational speed, they'll all be rotating, or I guess revolving in this case, revolving around the axis at the same speed because it's a solid object. Does that cover what you said? Okay. All right. All right, anyone else? Oh man, I see so many people wanting to participate here, but I think we're just going to move on, right? Oh man. Yeah. Oh, Mr. Fair, I wanted to say something. I know. No, pick me. Okay, fine. We'll move on. Okay. Yeah, okay. Accelerating with a constant speed. When we had first talked about vectors and scalars, we had distinguished between velocity and speed. Someone please remind me, what is the difference between velocity and speed? Or which one is a vector or something? Yes. Velocity is a vector, speed is a scalar. Yes, indeed. Okay, what else can we say? What is the distinction between vectors and scalars? Yeah. Yes. Okay, other people. Okay. All right. Don't feel bad. Everyone's just so excited about sharing in physics, right? Okay, so yeah, people are just busting out answers all over. One of them has direction and then one does not. Okay? The one that has direction that's important is the velocity, or vectors in general, but velocity has direction. Speed, which is a scalar, does not. Okay? Going around a bend, So you're driving your car, you go around a bend, you have a constant speed but a changing velocity. Now, what do you mean by that? Well, let's say, we'll assume most of you have driven before, and you're driving along and you put on the cruise control. And what does the cruise control do? Keeps you at a constant speed. Oh, good, you didn't say constant velocity. You say, oh, well, what's the big deal? Well, we'll see. If we're at a constant speed, then as we're moving forward, we're not going faster or slower. Say, sure, yeah, no big deal. And we're going at a constant velocity. Yeah, sure, no big deal. But then as we go around a curve, we're still going at a constant speed, right? But are we going at a constant velocity? Well, the screen says no. Okay, so why is that? Why are we not going at a constant velocity anymore, but the speed is constant? Well, no, actually, we are accelerating. You say, wait a minute, we're going at a constant speed. How can we be accelerating? Okay, well, what did we say is the distinction between speed and velocity? Yes, dear?
Direction.
Direction, yes. Direction is the big distinction between speed and velocity. If we're going around a curve with our cruise control on, we're not speeding up or slowing down. But we are changing velocity because we're changing our direction of motion. So imagine you're going forward and then you're going around a curve, let's say to the right. You weren't originally moving to the right, but now you are. Okay, so your direction has changed. Even though your speed is constant, your velocity has changed. And as was mentioned just a moment ago, that means we're also going to be accelerating, because if there's a change in velocity, that means there's an acceleration. Okay? Acceleration, that means there's going to be some type of force involved. Maybe there's more than one force. We're going to start off with some kind of simplified scenarios where there's just going to be one force causing this motion in a circular path. Okay? So if you are the red car, instead of going nice and forward like this, you're veering to the left, and that means there is going to be a change in velocity. You are accelerating in this direction. So we already talked about this equation. Speed is distance over time. This is the tangential velocity equation. If we're talking about going around in a full circle, the circumference divided by period, it's 2 pi r divided by capital T. That is the tangential speed, or v sub t. Now we call it tangential speed, but then we go ahead and use the v on here just because, okay? V tangential. Because the acceleration and force are for curving motion or circular motion, we have special names for them. Okay, we've already said about the word tangential, and we defined that last time in terms of a line that is tangential to a curve will just touch that curve once. Okay, so on the previous slide, tangential velocity would be the velocity right here going this way, to the left. The tangential velocity on this car right here is going straight up. Tangential velocity going here is up and to the left. That is why the velocity keeps changing, because the direction is changing. If you just say, hey, it's tangential, then we take that into account. Anywho, the acceleration is called centripetal. Centripetal. And we'll see what that means in just a moment. But here's the equation that goes along with it. Centripetal acceleration, A sub c, is equal to v squared over r. Okay. We can also see that as 4 pi squared r divided by t squared. And you might say, where did these equations come from? Okay, the derivation for this equation is kind of complicated. I've never really seen a good textbook's version of a derivation. So this is one of the very few equations I won't bother deriving for the class. It typically just confuses people more than anything else. So I'm just going to ask you to please accept this one. If you would like to talk to me about it in more detail, we certainly can. And I'd have to draw out a bunch of pictures. Okay, v squared over r is the centripetal acceleration. So where did this one come from? I can show you where this one came from. We just said that v is 2 pi r divided by t. Well, if it's v squared, that's going to be 2 squared pi squared r squared divided by t squared, yeah? Okay? But then we also have to divide through by r. So it's this whole mess is squared. So that's 4 times pi squared times r squared divided by t squared, all of which is divided by r. Okay? So one of those r's is going to cancel out on top with the one on the bottom, and that's what we're left with. 4 pi squared r divided by t squared. Okay? So that's the derivation for this one. Most of the time, it's just fine to go along with this, but I like to show the most fundamental equations to really understand how things work. And we'll see that is important later on. Centripetal force, well, force equals mass times acceleration. So centripetal force is equal to mass times centripetal acceleration, which is equal to mass times v squared over r. And if I wanted to write it out, I'd say mass times this business up here, 4 pi squared r divided by t squared. Okay, and you don't have to worry about these equations in terms of memorizing. I mean, once you get used to them, it's not that difficult to get the v squared over r thing, but these would be given to you. I wouldn't expect you to have to memorize these things. Okay, so those are the equations. If we talk about the centripetal force, we'd say, what does that mean? You got the equation okay? Was there a question? Sure. Okay. I'll just start talking about the next slide. Some textbooks, and some teachers even, do not mention the centripetal force concept. Reason for that is because they're concerned that will just confuse people. It's not like they're denying the existence of a centripetal force. It's just that they don't want people to think that's an additional force. The centripetal force is the reason that the object is going around in a circular path. Okay? It's the net force acting on the object. Okay, so the net force towards the center of the circle that causes uniform circular motion. Okay, so we had already used things, let's see, and it's in newtons. We had already used this symbol before. What does this guy mean? The sum of, yes, okay, sigma, sum of the forces, right? But prior to this, we've always said the sum of the forces on the y-axis, or the sum of the forces on the x-axis, right? And then we would list them out, oh, here are all the y's, here are all the x's, okay? If we're talking about an object that is going around in a circular path, and we just showed that the velocity is changing direction, it makes sense to say the acceleration and the force are changing direction. Can we reasonably say, oh, the sum of the forces on the x-axis? Well, a split second from now, some of those forces are going to be on the y-axis. Okay, so you say, oh, the sum of the forces on the x and the y-axis. Then the sum of the forces only on the y-axis, and so on. That would get way too confusing. So what all we're going to do is say the sum of the forces toward the center of the circle. That's what centripetal force means. So instead of saying the sum of the forces on the x or the y or the whatever, we say the centripetal force. We're talking about all the forces that cause the circular motion. So whenever we're going to be drawing a free body diagram, we'll list out the actual forces. We'll say, oh, the thing that's causing this circular motion is this force or that force. We would never, ever, ever put, oh, the thing that's causing this force is the centripetal force. Okay, because the centripetal force is not its own force. It's merely the sum of the forces that cause the circular motion. You say, okay, well, what does that mean? What other forces are there going to be that cause this circular motion? Okay, other forces, these are some of the most common ones. Tension, friction, gravitational, applied force, sometimes a normal force. Okay, all these different forces. If you recall a number of slides back when we said, hey, give me some examples of circular motion. What were some of the examples of circular motion? kicking a ball. Okay, and what was the object undergoing the circular motion? The leg, right, okay. If we want to focus just on the foot, though, because that'll make a nice, easy circle, obviously the leg is going with it, right? Okay. If, let's say, the foot, and, oh, geez, this is a little weird. If the foot, why is the foot going around in a circle? I was about to say, what if the foot somehow became detached from the leg, but that's not really how I wanted to start this conversation here. I really wish you had chosen a different example first, but okay. If, gruesomely, I guess, for some reason, as you're kicking the ball, maybe this is a new thing for the next Saw movie or something, the foot comes detached from the leg, what is the direction that the foot would move in? Oh, I guess we could talk about the shoe coming off. Not nearly as morbid, but why didn't you say that like 30 seconds ago? Okay, yeah, that's much better. The shoe comes off, not the foot. You freak. Freak being, not you. Me. Okay, so the shoe comes off, much nicer. The shoe comes off, and what direction is it going to go in? Is it going to continue going around in a nice circular path?
It's going to go based off of like the last direction that it was originally going in. So if
Oh, okay. Hold on, let me repeat that. So it's going to go in the last direction it was just going in before it was released by the foot, right? Go ahead.
so it would be like a straight path. So say it stopped at the very end, like the shoe would fly up.
Right. Okay. So if your foot is moving through a full half circle, most feet don't, but if we're pretending it does, okay. So at the very highest point, as we're heading our foot straight upwards, if we release the shoe, it would go straight upwards. What happens if the shoe somehow came off at the lowest point of the circle, just as you're kicking the ball? Which way do you think the shoe would go? Along the horizontal, right, along the ground. Okay? Okay. There was another hand up? Yes.
The shoe would move in a straight line tangent to the circle of motion.
Okay, the shoe would move in a line that is tangent to the circle. At that particular point, wherever it was released from the foot, it would go off on a tangent line. Right. Okay? Good. Other examples of the circular motion.
Throw it in the ball.
Throwing a ball. Okay? So, what allows that to be circular motion?
It's a smaller part of the circle, but it's part of the circle. And putting your arm back.
Okay, and we're swinging, so we're pulling the arm back. Let's get a real nice visual by doing a softball pitch. Okay, people have seen a softball pitch. You know, goes around kind of a windmill thing, and then there's the release. If the pitcher is not releasing at just the right point, then it could go flying upwards or flying downwards or whatever, right? She's got to release at just the right point so it goes, so the tangential velocity is nice and forward. Okay? Now, in both of these situations, what is the cause of that force? What is the cause of the force on the ball? What is the ball released from? Or what is the shoe released from? The person, either one of their limbs, yes? Okay. So in this case, I guess you could argue that there's an applied force or a tension force. I was thinking more along the lines of if people said, oh, the Earth goes around the sun, that's circular motion, right? Okay. What is the cause of that circular motion? What is the force? Gravitational force, yeah. If gravity were somehow turned off, what would happen to the Earth? Would it keep going around the sun? No. It would go off how? Into space, yes, but direction. Would it go straight away from the sun?
Depends on where gravity's
No. Well, okay, the specific direction would depend. But my question was, would it go straight away from the sun? No. Okay, it would go in the path it was last moving. It would go tangentially, right? Okay, it wouldn't spiral outwards. It wouldn't go straight away from the sun. It would just continue moving off in whatever direction it was most recently going. Okay, All right. Give me some other examples. Let's see. Um, if I were to be driving a car, we already used that example, and I go around a curve, what is the reason that I can go around this curve? What is the force acting on me? Well, it is it's centripetal force, as in its circular motion, but we don't ever say, oh, it's the centripetal force. We'd have to say, oh, it's the whatever that is the cause of the centripetal force, right? Okay, so let's think of what we just discussed. Is it gravitational? In order to go around a curve, do I have to have a really massive object right next to me? And I gravitationally go around? No. Okay, let's see. The other one I used was tension. Okay, do I have to stick my arm out the window and grab hold of like the stop sign and use that to spin me around? Is that going to work very well? No. Okay, not very good. Okay, so what does allow us to go around the curve? Friction, yes indeed. Okay, it's the friction between the wheels and the road that allow us to do this. You say, oh, why is that? Well, how about this? We know how much it's been snowing and icing recently, yeah? Okay, why is it that we've had days off or delays or whatever? Yes? Because there's less friction, right? So if you're trying to move along, if you're trying to stop or slow down or speed up or whatever, you can't do it because of friction, right? Sure. But also, if you're trying to go around a curve and there's not enough friction, are you going to go around that curve? What's more likely to happen? You're just going to keep going straight forward, right? Okay? Maybe you'll kind of start turning, but you're not going to turn enough, so you could just go right off the road or crash into someone or whatever. Okay? So yeah, excellent, excellent. Okay, let's talk about this. Uniform circular motion example. Okay, a 0.013 kilogram rubber stopper is attached to a 0.93 length of string. The stopper is swung in a horizontal circle, making one revolution in 1.18 seconds. Okay, so here's a kind of a visual. What's going on here? You're spinning it around. Imagine he's got safety goggles, of course. Find the speed of the stopper. Find its centripetal acceleration. Find the force the string exerts on it, and what is the cause of this force? Okay, go ahead, please. Okay, so I have drawn out the basic information from here. I've got my list of variables written out. Got my mass, got my radius, and got my t. That's my period. It says it makes one revolution in 1.18 seconds. Remember, folks, it's very important to be able to figure out what the period is versus frequency. If you got one, it's easy to get the other one, but you got to make sure that you're interpreting it correctly and say, oh, this is the period or this is the frequency. From here, I said it does something in this time period. Okay, so if it takes this long, that is going to be a period. That's t. Okay, we are looking for the v sub t, the tangential velocity, and the acceleration and the force. Okay, so I always like to start off by drawing a nice picture. Okay, we already had our picture up here with the side band, but I am also including a visual right over here. So this right here is the ball, okay, and we have the string here, and it's going around counterclockwise. Okay, so the ball is moving which way? At this particular point. Right, but at this particular point, it's going which way? It's going straight down. So this is going to be the tangential velocity, v sub t. Okay. What else can I list off on here? What is the direction of the force, do you think? And the acceleration? Okay. Yes, to the right. Okay. So the centripetal acceleration is to the right, and the centripetal force is also to the right. Now, a moment later, if we were talking about the ball when it's down, or I'm sorry, the rubber stopper when it's down here, then I'd have to just adjust these things. The velocity would be this way, the acceleration and the force would be that way. Okay, that's why we use things like words like centripetal and tangential instead of x and y. Okay, so let's go ahead and solve for the let's see, the speed of the stopper. So what can we do here? We've got our equation for speed. Tangential velocity is equal to the circumference divided by the time, right? So that's going to be 2 pi r divided by the period, okay? So that's going to be 2 pi, and the period is 0.93 meters, and that is divided by the time of 1.18 seconds. And what did we get for that, please?
4.95
Okay, 4.95. Is that what people got? Okay, okay, 4.95, and then that's meters per second. Okay, yes.
Why isn't it just distance over time?
Okay, well, it is distance over time, but think about what distance it travels in. And this is going to confuse a number of people if we're not being careful, and that's why I always draw out the thing. Okay? If we're talking about it spinning around, okay, if we're talking about it spinning around, then we're talking about it going like this all the way around here. That is the total distance it has traveled. Okay? So if you just see, oh, here's a distance, 0.93, right? That looks like a distance to me. Well, it's not that distance. Okay, that is the radius. Okay? All right. Let's see. So that's the velocity. So this is pretty much 5 meters per second. Okay? All right. B, find its centripetal acceleration. Go ahead and use a lovely green for that. Centripetal acceleration is d squared over r. Okay, we can plug it in our velocity there, square it, and divide through by the r. From there, I can see it's effectively 25 divided by 1. It's not quite that, but it's going to be about 25 meters per second squared. So that's like I've already checked it, right? Okay. If I do the actual calculation though, I could use this one, or I could use the original, or the more basic equation, 4 pi squared r divided by t squared. That would also get me the same information. Did anyone use this second equation? Okay. All right. What did you end up getting?
I got 26.
26.37.
26.36.
Okay. Got, let's say just 26. That's going to be meters per second squared. Now, someone said something else. Well, they did it wrong. Yes. Okay. Does anyone have a question on how this was figured out? Why don't you redo your numbers? If you use this version right here, make sure you squared the velocity and only the velocity. Okay. And if you're still not sure, please raise up your hand, or you can talk to me after I turn off the microphone. And then part C, find the force. Okay, well that's pretty straightforward. F centripetal equals ma centripetal, right? All we got to do is take this guy and multiply it by the mass. Yeah. Okay. Oh, I should have said this was an estimation. So that was an estimation. This guy is the correct answer. Just for clarification. So the 26 meters per second squared times the mass, which was 0.013 kilograms, is going to give us what? Okay, folks, this is like the easiest one to be able to get. Okay, so that's going to be 0.34 newtons. Excellent. Okay, it's supposed to be 3. Yeah, okay, 0.34 newtons. Okay. And then what is the cause of this force? What is the reason this stopper is going around in a circular path? And if we got rid of this force, it would no longer go around in a circular path. Yes. The tension, okay? The tension in the string here, okay? The tension right there. If we were to cut the string, or if it were to break, or if we were to let go, or something along those lines, it would just fly off in whatever direction it was most recently going. If it were right, let's see. If it were at this position, like we had mentioned earlier, if we were to let go, it would go off in that direction. Okay. This is an overhead view, so when I say it's going downwards, I mean it just imagine that's like a south. Okay. Okay. Questions on this? Delicious. All right. Let's move on to the next slide. Okay. Same scenario as before. We got the same mass and all this info. Now, how would velocity, acceleration, and force change if you doubled the mass but kept everything else the same, you doubled the string length but kept everything else the same, and then you halved the period but kept everything else the same? Okay, go ahead and try that, please. Okay, now that we've had a moment to try out everything, we see it's really the same information, and so we can just be using the same equations and see how things are going to be affected. Now, part A should be nice and easy because we're talking about doubling the mass and only changing the mass. Well, which equations have anything to do with mass? If I look up here, these are the some of the equations that I have, right? Which of those have force in them? Oh, I'm sorry, last. Which one of those have mass in them?
Force.
The force equation. Yeah, okay, fine. Okay, so if I double the mass, is that going to change the velocity?
No.
If I double the mass, will that change the acceleration?
No.
If I double the mass, will that change the force? Yes, it would double the force, right? Okay. So double the force. Okay, but everything else would be the same. Okay, so as we said, the only thing with force in it, or the only thing with mass in it, is the force. So we end up doubling the mass, we double the force, but nothing else. Now, if we're going to double the string length but keep everything else the same, how would that affect our velocity? How would that affect our velocity? It would be doubled. Why do you say that? Okay, if you plug it in, it's doubled. Sure. Okay. Yes, we can also go into a little bit more detail if we were to just kind of focus on this. If we say V is proportional to R, V is proportional to R, that means if we double one, we double the other one. Okay? Sure. Now, what happens if we, what happens to the acceleration? If we double the R, what is going to happen to the acceleration? Okay, so I hear someone saying doubled. Okay. Anyone else? This is a tricky, okay, someone said it's the same. This is a bit tricky because we can look at various versions of the equation and get different answers. Plug in. Okay, so which equation should we use? Well, here's a lovely equation for acceleration. A sub c is equal to v squared over r. V squared over r, if I double this r, the r is in the denominator, yeah? So if I increase that, then that means my acceleration should get smaller, yeah? So if I double the r, then that would mean this gets to be, okay, that'd be like this is half. Okay.
V,
Yes, go ahead.
so since V equals the 2 pi r, and the V is doubled when you put in the 2, and since V is squared, it'd be quadrupled, and then divided by 2 would just be doubled.
Okay, now the question was, what about the v? Because we just showed that velocity is proportional to the radius. Okay, so we double the v, that means we've got to double square it. So it means it's got to be a 4 up here. Okay, so the 4 divided by the 2, that actually means we're going to double the acceleration. Now some people might be like, whoa, what the heck are you talking about there? If we use our more fundamental equation, it's a little bit easier. Centripetal acceleration is 4 pi squared r divided by t squared. That's a square. Yeah. It's a square, quite. Okay, there's only one r right here, and it's in the numerator, which means centripetal acceleration is proportional to r. So if I double the radius, then I've doubled the centripetal acceleration. Okay, is that making sense? It's a little bit easier when we talk about in terms of the more fundamental equation. That's why I showed you the more fundamental equation. Okay, and then finally, what about the force? Well, force is pretty straightforward. As long as you're not changing the mass, it's going to go along with the acceleration. Okay, so if we doubled the acceleration, then that means we'll have to have also doubled the force. Okay, so if I double the string length, everything doubles. Hopefully that makes sense. Okay, and then finally, what if I cut the period in half but keep everything else the same? So just to make sure it's clear, I do have it written out here. Okay, so they're all doubled. Okay. If I cut the period in half, what will happen to everything else? If I cut the period in half, what does that mean about how long I take to do something? It's got to be done faster, right? Okay, I've got to do the same job but in less time. So I've got to be working faster, right? Okay, so that would imply that the velocity is going to increase, yes? Okay. So what would be the case specifically for the velocity? Okay, yeah, I would, I'm sorry, say it again?
The period was half and the velocity doubled.
Okay, yeah, if the period is halved, then the velocity would be doubled, yes. Okay, so I'd end up doubling the velocity. Okay, if the period is halved, then the velocity is doubled. Okay, which we kind of just worked our way through. Okay, what about this other part, though? What about the acceleration and the force? Okay, so someone is saying quadrupled. What do people think of that? Okay. Oh, one person said it would be quartered. Interesting. Okay. So, but we're pretty convinced that it's not just going to be done by a factor of 2, it's going to be done by a factor of 4, right? Okay. Let's work out a nice equation. Let's see, where did this guy. Okay, if we're talking now about cutting the time in half, how would that affect everything else? So, let's see, move everything away. Okay, so if I've got my acceleration centripetal is v squared over r. Well, there's not a time in there, or at least not explicitly. If I expand that out to 4 pi squared r divided by t squared, now I see what's important here. Centripetal acceleration, I'll rewrite it here, is 4 pi squared r divided by t squared. if I were to put 1/2 in front of this guy, then I know that 1/2 is going to be squared because the t gets squared, yes? So that's going to be 1/2 squared is what? 1/4, yes. Okay, so I'd have to put, so I have a 1/4 in the denominator on the right side. Okay, so I'm going to put a 1/4 in the denominator on the left side. What happens when you divide by a quarter? Or what happens in general when you divide by a fraction? You can just multiply by its inverse. Okay, so a divided by 1/4 is like saying 4 times a. So it would quadruple the acceleration. And just like over here, mass and acceleration do the same thing as long, force and acceleration do the same thing as long as you don't mess with the mass. You quadruple the acceleration, you're also going to quadruple the force. Good? Hopefully it makes sense. Okay. Okay, a few more things, and we've kind of already talked about some of them. Centripetal, I had already introduced this term, but I guess I didn't specifically define it yet. It means seeking the center, or center seeking. Okay, so if we have a string tied to a ball, or like in the case from before, the stopper or whatever, and it's going in a nice circular path. Why does it go in the circular path? You're spinning it around, yeah? What is the reason, though, that it goes in the circular path? It's not witchcraft. Well, it is being accelerated toward the center, and because there is this centripetal acceleration and centripetal force. Okay, but I mean, what is the agent behind this force? Why is this ball going around in a nice little circle? Yes. Well, the person. Right. Not just physics. Thank you. The person is pulling on the string, so the tension in the string is causing this to go in a circular path, right? So the tension is there. That's the reason it goes around in a circle. What if I took the string away? What if I removed the tension? What if it breaks? What path would this travel? Okay. Would it go inwards like A, B, kind of like the direction C, D, D? Okay. Anyone say it would go in direction A? Raise your hand, please. Okay. B, raise your hand, please. C, raise your hand, please. Okay, that's most people. D, raise your hand, please. And E, raise your hand, please. Okay, some people forgot their hands. That's okay. I was talking about your foot falling off earlier. I just some people took what I said a little too far, I guess. No, it would be C. Yes. Why would it be C? Okay, because that line is tangent to the circle. As soon as this breaks, there's no reason it would continue to go in a circular path. It's just going to go in a nice constant direction because of the object's inertia. Okay, so it goes in path C because of the inertia of the tennis ball. Okay, so centripetal versus tangential. The ball would like to go in a straight line. And by like to, I mean it has inertia. Okay, but the string was pulling back on it. It was pulling it inwards. The string is effectively an outside force. There's an outside force, that means, according to Newton's laws, there's an acceleration. So at this moment here, words go away. All right, way up here. If the ball is right here, the direction of motion would be like this way. the force and the acceleration would be pulling it inwards. Okay, that's the reason for the curving motion. If we're talking about a nice perfect circle, then the force and the acceleration are going to always be perpendicular to the velocity. In a nice perfect circle, or effectively a nice perfect circle, the force and the acceleration would be perpendicular to the tangential velocity. If we're not talking about a nice perfect circle, they're not necessarily going to be perpendicular. But we'll save that for later on when we talk about some things in terms of gravity. Now, imagine for just a moment that you're driving your car and you're driving in the forward motion and you speed up. What is the direction of your motion? We just said it's forward. What is the direction of your force? Or what is the direction of your acceleration? How about that? Forward, okay? So that means you're going to be speeding up, okay? If you're driving your car forward and you hit the brakes, what is the direction of the force and the acceleration? Yes, backwards, okay? So that causes you to speed up or slow down because it's along the same axis. If you're driving your car and there's this force that's pushing you left, just 1 second, please. If there's this force that's pushing you left, is that going to cause you to speed up or slow down? No, because independents are perpendicular vectors. That is why you can keep going around at a nice constant speed, even though you're changing direction, changing velocity. Good. Okay, so circular. This is our last example problem that we're going to be having. We have a 20-gram ball, so I did have to convert that into kilograms. Here is the radius, that's 0.5 meters. Force is 0.75 newtons. What is the acceleration? What is the velocity? And what is the period going to be? So, how could we do this? What should we do? Okay, so we have our equations that we can use. The fact that we have force, remember there's really only one set of equations that will deal with that, some type of F equals ma or a version of that, right? So F equals ma. Okay, right, solving for A. Okay, I'm going to have acceleration, and that's the centripetal acceleration, is equal to F over m. So that's just going to be 0.75 newtons divided by 0.02 kilograms. It's a small numerator, but even a much smaller denominator, so it's going to be a larger number than you might have expected. What is the acceleration going to be? Okay, say it again, please. 37.5 meters per second squared. Yes. Okay. And then I'm looking for my velocity. I could go back to the real fundamental versions of the equation, or I could just say, hey, I've got the centripetal acceleration, and I've got the radius. Let me just use centripetal acceleration equals v squared over r. Yeah? Does that make sense? Okay, so solving for v, I'm going to get v squared is equal to r times a centripetal. So if I take the square root of that, there I am. So I plug in the values. Okay. We said r is 0.5, and the centripetal acceleration, and that was 0.5 meters, I should say. The centripetal acceleration was 37.5 meters per second squared. Notice it'll end up being meters squared per second squared, and we take the square root, that would be meters per second. That's good. Okay, so what's half of 37.5? Okay, 18 point something, and then we take the square root of that. Okay, so V equals 4.33, and that'd be meters per second. Okay, and then finally we're looking for the T, that's the period, yeah? Okay, so what equation can we be using there? Okay, so 1 over F was volunteered. Now, I don't want you to get confused. The F in the T is equal to 1 over F equation, I always write that as a lowercase f. I'll put it up over here in red. Okay. F is equal to 1 over T, and T is equal to 1 over F. This T here is a capital T, that's period. This F here, in each of the equations, is a lowercase f. That is not force, that means frequency. We don't actually have the frequency. Okay? This force right here, or this F right there, is a force. Okay? So, good idea, but that doesn't work. Okay, what can we use, though? Say again? We can use 2 pi over T, yes. Okay, and that equals what? Okay, velocity is equal to 2 pi r divided by t, yes? Okay, solving for t, I can just, well, I call it the switcheroo. That's probably not what they call it in math class, but anyhow, t is equal to 2 pi r divided by v. Okay, just had to, it's cross multiplying and then dividing, but I'll just call it the switcheroo. Anyhow, so 2 times 0.5, that's the radius, that's going to just be 1. That's going to be equal, and then multiplied by pi, so pi divided by the velocity, which was 4.33 meters per second. So it's about 3 divided by about 4 1/3, not exactly, but pretty close. What do we end up getting?
0.73 seconds.
Okay, 0.73 seconds. Good. 0.73 seconds. Excellent. Okay. Let's scoot down. We have a 550 kilogram car. It's driving around the track at 60 meters per second, and here's the radius is 0.75 kilometers. Notice I did put it in meters. That is important. What is the centripetal acceleration? What's the centripetal force? And what is the reason for the centripetal force? Okay, so we have all of our information. We don't care about any of that. Okay, what do you want to solve for first? Do you want to solve for acceleration or for the force? I would like to solve for the force. Yes, okay, we can do the force first if you'd like. Okay, right, okay, so, well, force, let's get it in the color. Force equals mass times acceleration. Well, if I had the acceleration, then there I'd be, right? Okay, well, fine. What else does it equal? Mass times v squared over r. Yeah? Do I have the m and the v and the r? Yes. So that's going to be 550 kilograms. Okay, times v squared, that's going to be 60 meters per second squared, divided by the r, which is 750 meters. Okay? Okay, so we're tapping into our calculators right about now. Should be force in the thousands, I assume.
2,640.
Say again?
2,640.
2,640? Okay. 2,640 newtons. Okay? Sounds splendid to me. Okay? And if we were to solve for the acceleration, we could take this value and divide through by the mass. Or we could say acceleration is v squared over r, and just say 60 squared divided by 750. Okay, either way we'll get the same answer. What is that going to be? Okay, say it again, please. 4.8 meters per second squared, right? Okay, so 4.8 meters per second squared. Okay, And then the final question was, what is the reason? What is causing this force? Okay, so I have this image here. This force is going inwards, but maybe you can't really tell. This is supposed to be F sub question mark. Okay, as in what is the reason for that force, yeah? And here's my acceleration. I just know that they're inward. I know they're centripetal, but I don't know the actual reason it's going around. And here's the velocity. Okay, so what is the actual reason that the object is going around in the circle? In other words, if I remove this reason, it would no longer go around in a circle. All right, not string. String was the case for the first one. Okay. Other people said friction. Yes, friction is the reason here. You imagine, like we mentioned before, you're driving along, and you want to go around this curve. Okay, so you just turn left, you turn right, whatever. Okay, and you're able to go. What if it's really icy out? If it's really icy, then you're not going to be able to make that curve very well. Okay, reduce the coefficient of friction. That means you're reducing the centripetal force. We'll talk next time about what we can do in those situations. What road engineers have done to help us be able to make turns while still going relatively fast. Okay, any questions on anything? Okay, here are the answers written out like this in case you'd like it that way. And then the next slide is just summarizing all those things: centripetal acceleration, centripetal force, and tangential velocity. But that's something perhaps you can do on your own. Okay? Physics is delicious.